Okay, well, hello everyone, welcome. It's a great pleasure to introduce our guest speaker today, who is a research scientist and professor at the Joint Center at for Quantum Information and Computer Science. Good. And you also had research positions at, I think, Caltech, University of Waterloo, and Copenhagen. And yeah, he's going to be talking a little bit about quantum algorithms and cryptography. So please welcome Dr. Gorjan Alagic.
Okay, thanks guys. So I thought I'd talk a little bit about cryptography and quantum, what the two things have to do with each other. I hope this will be kind of pretty interactive, so stop me if you have questions, if something's unclear, or if you want to ask some related questions, and I'll try to set aside some time at the end. So first of all, maybe just a question. How many of you know or have heard of the one-time pad? Okay.
I know it took CSV 2 years ago.
Okay, good. Okay, so let's look at so here's the question. The question is, how to send secret messages, okay? Which is one part of cryptography. So let's suppose there's two people, Alice and Bob, we'll call them, and they want to be able to send secret messages between each other. So the first thing that Alice and Bob should do is they should agree on some secret random numbers, okay? And they need to be numbers between 1 and 26. So let's suppose that they agree on the following sequence of numbers. Let's say 3, 2, 16, 14, 20, and so on, okay? And we're going to call this their secret key. Okay. So they do this somehow. We'll talk later about how they might do this. And now they have this secret key and they go their separate ways, and now at some later point, somebody wants to send a message. So for example, let's suppose Bob wants to send a message, and just for simplicity, let's suppose the message is just a single letter. Okay? So suppose Bob wants to send the letter D. Okay? So what should Bob do? So Bob should first convert this letter into a number between 1 and 26, right? So I guess it's A, B, C, D, so it's 4. Then Bob will take the first number in this list and use it up. What he'll do is he'll add it to 4, he'll get 7, and then he'll send 7 across to Alice. Okay. So just to be clear, what I'm assuming here is that this number up here, these numbers up here, are not known to anybody except Alice and Bob, okay? But these numbers, the ones that are later sent between Alice and Bob, everybody can see. Okay, so it's very important that you cannot figure out from this number what the message was. So for those of you just arriving, we're talking about how to send secret messages. We said the two parties, Alice and Bob, should first agree on a bunch of secret random numbers, and then when Bob wants to send, let's say, the letter D, he should first turn it into a number, it's the 4th letter of the alphabet, and then add the first number in here, get 7, and send it back to Alice, or send it to Alice. Okay, and then Alice knows what to do. She'll look at the first number, she'll undo what Bob did, she'll get 4, and then she knows that that's the letter D. Okay, so I claim that this is a perfectly secure way to send messages, and I want to kind of briefly argue why that's the case. So let's maybe talk about random numbers, or maybe actually uniformly random numbers. Between 1 and 26. Okay, so what does this mean? So you've probably had a little bit of probability, at least, maybe a lot. So if I say pick a uniformly random number between 1 and 26, what's the probability that that number is, I don't know, 3? 1/26, right? In fact, that's true for any particular number between 1 and 26. That's what it means to choose the numbers uniformly at random. Okay? So what I want to argue to you is that anyone who sees this number here and doesn't know what these numbers are, to them this number will also appear to be uniformly random. And at least intuitively, that should mean that the number carries no information. Right? But let's look at that. So let's suppose we want to send the letter D. Okay. This generalizes, but let's just suppose it's D for now. So what's the probability that the encrypted number, or the encrypted message, is, let's say, F, or I don't know, 6? Well, I guess that's just the probability that the secret key is, let's see, so 6 minus what number this letter is, right, 4, so that's just 2. Does that make sense? Right? So if we're sending D and the encrypted message turns out to be 6, that means the number must have, the secret key must have been 2, right? That's what takes us from D to 6. So, you know, the probability that the encrypted message is 6, if you don't know what this is, right? Because that's the situation of the adversary, is just the probability that the key is 2. But what is that? It's just 1/26, right? Because that's how we chose the key. I mean, this is just an example, right? But in general, yeah. And this generalizes, right? If we want to send some letter, you know, little x, which could stand for any letter of the alphabet, and the encrypted message turns out to be, you know, y, well, that's just the probability that this is y minus x. You know, so this is just the probability that the secret key is some particular number, right? But we already said that that's 1/26, so that's uniform. Okay. So there's one minor caveat, which is that this number could be less than 1, right? Because it's subtraction. It could, in fact, also in general be bigger than 26. So this is actually done modulo 26. How many have seen modular arithmetic before? It basically just means wrap around, right? If you go past 26, you just wrap around to 1 and continue again. Same thing. Okay, so let's do another example. Let's suppose Alice wants to send the word help. So what's this? So let's see. So first convert these to numbers. I think this is 8, 5, 12, and 16. So then what Alice will do is just add, now she'll take multiple numbers from up here. She needs 4 to use up, so she'll use up these 4 here. So she'll add 2, 16, 14, and 20. Right, so she'll get 10, 21, 26, and 36. Okay, but we need to end up with a number between 1 and 26. So what should we have instead of 36? 10, right? Yeah. So we'll subtract 26 and we'll get 10. So Alice should send those numbers. So she'll send across 10, 21, 26, and 10. Okay. And then Bob will just, you know, undo the operation that Alice did. So he'll subtract the key. So the key is 2, 16, 14, and 20. So Bob will get 8, 5, 12, and -10. But what's -10 mod 26? right? So we went 10 off the left side.
So it'd be 16.
It's going to be 16. And then Bob can convert this to. Okay. And then now if you want to argue that, well, here again, somebody just looking at these numbers is going to have no idea what the message was. Basically, that's just you repeat the same argument for every single number. You know, so the probability that this particular number has some value is just the probability that that key is some different value. But that's always 1 over 26. So these all look like just uniformly random numbers to anyone who sees these messages but doesn't see the secret key. Okay? So this is called the one-time pad. Okay. So any questions about that? Okay. So this is a, you can actually give a mathematical proof that this is a perfectly secure way to send secret messages. And this was kind of a sketch of how that proof might go. So now the question we have is, I guess, how do Alice and Bob get these shared secret numbers? Okay. That's kind of, so if we want to send perfectly secret messages, we've kind of reduced the task down to that task, right? So once they have those, then they know what to do from there, but I guess it's not clear how to do that. So the sort of second question is how to exchange, or maybe how to agree on a shared secret key. And by secret key, I just mean a bunch of numbers. If we're going to work directly with the alphabet, it should be numbers between 1 and 26. If you're going to use bits, they can just be bits, whatever. Just some numbers. Okay, so basically there are kind of three methods I want to talk about. The first method, which is the only method we had before the 1970s, was the meet in person method. Okay, so people have been sending secret messages since, I don't know, probably since language. And the only way we knew how to do that before the 1970s was to meet in person, agree on these secret numbers. Alice writes them down, puts them in her pocket. Bob writes them down, puts them in his pocket, and then they go their separate ways. Okay, and then they make sure nobody else, they make sure nobody was listening, they make sure nobody can see their notes, and then they're kind of in this situation. But it's kind of annoying that they have to meet in person. So, as you all know and experience every day, you don't have to do this anymore, right? Like you're constantly, well, okay, maybe you're not banking, but you're like going to Amazon and ordering something. You're doing things that involve exchanging secret and also authentic messages, using your credit card number or whatever, and you're not having to like drive to Amazon headquarters or anything, right? You can just go there and it works. So, and that is all because of discoveries that happened after the 70s. And so the second method is, well, to use math, and a little more specifically, to use something called one-way functions. And I'm not going to be super precise here, but okay, I'll talk about that method a little bit. And the other method we now also know about, so that one was discovered in the 70s. The other one, a few years later, which is to use quantum mechanics. Okay, and maybe I'll also be able to talk about that one a little bit. Okay. So, yeah, so let me talk about the use math approach. And maybe let me go over here. Okay, so what's the setup now? So now let's suppose again we just have Alice and Bob. Except, you know, Alice and Bob don't share anything now. Okay, they don't have any secret information in advance, and what they want is for both of them to produce the same key at the end. And moreover, for this key to be, you know, uniformly random, let's say a single uniformly random number, that'll do, right? If we can do that once, we can just repeat the process over and over again, generate as many as we want. And it's important that nobody knows what that key is, except Alice and Bob. Okay, so how do they do that? So here's one process they might do. So they might agree on a number G, and here I'm just going to deal with integers. Okay, so they're going to take some integer G, maybe I don't know 5 or 17 or something, and they're just going to announce it. Okay, so everybody knows what this number is. Then Alice will pick a random number. Okay. Then she's going to compute G to the A, okay, just usual exponentiation, and she's going to send over G to the A to Bob. Okay. Not G and A, right? Because then she's revealing her secret. It's crucial that she takes G to the power A, writes down what that number is, and then she sends it over to Bob. Okay. Then Bob will pick a random B. Okay. He'll compute G to the B, and then he'll send that over. Okay. So basically the same thing that Alice does. In fact, they can do it at the same time if they want. Okay. So then, what Alice will do is she will take the G to the B that Bob sent, and she will take it to her secret power. Okay, and what's that? G to the AB, right? And that's going to be her key. And then Bob will take what Alice sent, G to the A, and he's going to take it to his secret power B, and he will also get G to the AB, right? And that will be his key. Okay? So at least as far as they will definitely arrive at the same value, right? It'll be a randomish value, probably, right? Because, you know, it's G to the product of two random numbers. Two random numbers are random, so like whole thing will be random, believably. Okay? Okay. So does this work? That's good. Good here.
So how can you make sure people don't determine what A and B are based on G to the A and G to the B?
Okay, good question. How might they do that? No, you wouldn't have to factor.
You use a computer
Okay, to do what?
to just go through each scenario.
Okay, so suppose you go through each scenario, and let's suppose Alice and Bob are pretty clever. They're going to pick their numbers, let's say, between 1 and, I don't know. They're going to pick very large numbers, let's say with hundreds of digits, or maybe 1,000 digits. So now trying every possibility, right, is going to take way too long, right? Is there something else that could be done? Thank you, yes. Why not just take log base G of this value? The result is A. So I just broke the scheme, or you just broke the scheme. Okay? Right? Okay, so this scheme is broken. This does not work. Okay? However, a simple modification does work. And that's to do this in modular arithmetic. Okay, so we're going to pick some number P. Okay, it needs to be a big number, but smaller than what G to the A and G to the B will in general be. Okay, so So all these computations will now be modular arithmetic, just like before. If you got past 26, you're going to come back around. So this will also be done mod p and mod p. And now, it turns out that computing the logarithm from this is, as far as we know, hard. Okay. So if I'm computing the log of g to the a, I know how to do that. You all know how to do that. You can write a fast computer program for doing it. But if it's this computation, if it's modular exponentiation, then there's no algorithm that can run even on, if these things all have hundreds or even thousands of digits, which is totally doable using phones or any computer, then inverting this operation, even using all of the computers networked together on the planet, would take hundreds of years, as far as we know, using the best known algorithms. So, so this is called Diffie-Hellman Key Exchange. And it's based on the hardness of computing discrete logs. Okay, discrete log is just the name of the function that takes a value like this and then computes a from it. Okay? So Diffie and Hellman are two cryptographers who discovered it in the 80s, and basically more or less any time you make an internet connection, this is the algorithm that happens. Yes?
Would it matter what the value of p is and who knows it?
Yes, but, well, not the second part. So G and P are both public. P needs to be much bigger than G, should be a prime number, stuff like that. There's various details for how you pick this. In general, it gets much more complicated, but this is kind of the basic idea of how it works. Yeah. But yes, G and P are both known in public. They're like the parameters of the scheme, so you just announce those to everyone in advance. Okay. Yeah, so like TLS uses this. TLS is like the secure protocol in browsing. If you go banking or whatever, this is what happens. First, this is how you negotiate a secure connection. And now from here, you could do the one-time pad, right? If you have enough of these numbers, there's more efficient things we can do, but in principle that we can do that. Okay. So just, yeah, so this is kind of this approach. I do want to say a little bit about the quantum mechanics one, but maybe just a few comments about this first. So, I mean, I guess maybe when I want to kind of get across that this is kind of amazing. Maybe let me describe it this way. So, like none of you before coming here like met up with each other and exchanged any secret numbers, right? Presumably, right? Okay. And now suppose you don't get your phones out, because I know you could always start messaging each other or something, but there's no phones, okay? And now what I'm saying is that, despite the fact that none of you agreed on any sort of secret code in advance, like any two of you could stand up, right, start talking to each other. Everyone can hear what you're saying, but after just two messages, like two sentences back and forth, it'll be math, like you'll be saying numbers. After that, you'll be talking in code with each other. And despite the fact that everyone was listening to everything you said, after those first two messages, we won't have any idea what you're saying, right? But you will know, and you'll be able to communicate with each other secretly, right? That's kind of weird, right? Like it seems like it shouldn't be possible to do that, but it is. And in fact, that's how like internet connections work, secure ones at least. Okay. But the crucial assumption. So let me. The crucial assumption was that computing this d-log, discrete log function is hard, even for the most powerful supercomputer. Alternatively, there's another scheme that you could use to exchange keys. It's called RSA. It's based on, those are the 3 letters of the, oh, actually, I wanted to make a different comment first. I forgot about this. So how amazing is this? It's so amazing that there's a very, very nice anecdote from the 70s about an undergrad. His name is Ralph Merkel. He was an undergrad at Berkeley. Okay, he was taking a cryptography course. We were still at this stage. Okay, so this is before this stuff was known. And he proposed a project to his computer science professor at Berkeley, saying that he wanted to explore ideas for 2 parties to do secure communication over a public channel, right? Exactly this problem, right? Like 2 people, they haven't met in advance, they don't have anything, they just want to communicate secretly, but all they have is a public channel. Everybody's listening. And his professor told him that that is obviously ridiculous and can never work, and to pick a different project. And so actually he quit the course and he did come up with some interesting protocol. And a few years later this came out. So it's not just me saying it, like if you were a Berkeley computer science professor, like cryptography professor in the 70s, you thought this was not even possible. So anyway, so it's kind of amazing, and it's why the internet works. So alternately, there's another scheme called RSA, which uses kind of different functions and a different approach. And there, the relationship between the secret random numbers and the kind of public message is actually just multiplication. Okay? So in this case, it was kind of so alternately factoring being hard is needed. So like, if you like, in this case, it was important that like compute going from A to G to the A mod P, that this was easy, right? But going from this back to A was hard, right? So that's the sense in which this is a one-way function, right? You can go this way, you can't really go this way. In the case of factoring, it's something like, I just have a bunch of numbers, x1, x2 through xn, and then it should be easy, and of course it is, to just form their product, right? Multiply them all together. But the other direction should be hard. So if you think about it, if you're given a really big number, let's say it has 1,000 digits, and you're asked to write a computer program for factoring it, I mean, what would you do? Okay, actually, that's a good question. What would you do?
You use a computer?
You would use a computer, but what would you, because the computer is just a box sitting there. Unless you tell it what to do, it kind of, yeah.
I'm thinking you start from like 2 and by each one.
Yeah, don't be clever. Just, is it divisible by 2? Is it divisible by 3? Is it divisible by 4? It turns out that the actual best known algorithms after, decades of, thousands of very clever people studying it, the best known algorithm is not much better than that one. So, yeah. So that's the other assumption, and a lot of internet connections, sort of the remaining internet connections are based on this. So they're all based on one of these 2 assumptions. Yeah.
So what makes that the code on the left so secret is like at the end making it G to the AB. So like anybody listening in, they'll know G to the A, they'll know P,
G to the B.
but they don't know that you're taking G and then putting it to the AB, and that's what makes
they know what you're doing. So this is a crucial thing. The protocol is public. I mean, in fact, I just told you what it is. So you all know what the protocol is. So the hardness of breaking it has to just amount to not knowing and not being able to compute these random numbers and not being able to conclude what the final key is, right? Purely from seeing these two messages, right? So actually showing that this is hard based on some assumption, that's involved. But I'm just giving you sort of an idea. Yeah.
A quick question. So the reason that I don't know too much about discrete logs, but it makes it difficult because you don't know how many times you've wrapped around p.
Yeah, you can think about it that way.
Is
Yeah,
that
something like
pretty
that.
much?
Yeah, or at least that's why the usual logarithm doesn't help. Okay, so in the remaining few minutes, I'll try to talk about idea 3, which is how to use quantum mechanics, and here there are kind of two key principles of quantum mechanics, which I'll describe only briefly and very informally. One of them is no cloning, which says that you can't copy quantum states. Okay, what's a quantum state? I don't know. Let's not worry about it. But it's just something that we, unlike with classical information, we can't copy. So when I say classical, I mean not quantum. So like numbers, images, text files, stuff like that, you all know how to copy, no problem. Turns out that if it's a quantum state, if it's a piece of data living on a quantum computer, there isn't actually a way to copy it generically. That's the no cloning principle of quantum mechanics. Physics is weird. The other one is called, let me call it this way, no looking without disturbing. You also know how to, like open up a text file, look at an image, think about a number, nothing weird about that, and it's not going to change it, right? You open up a file, the file's not going to change because you opened it, right? Because you looked at it. Quantum data, different. You want to look at it, you want to see what it is, you want to understand some property of it, you'll have to actually change it in the process. Okay. You can think about, like measuring where the electron is in some orbital. Okay. Until you look at it, it's in some complicated quantum state. When you look at it, it actually stops in one appears in a single position. You actually changed it somehow. Okay, so let's just, let's see if we can use these two principles to argue that maybe Alice and Bob can exchange a key. I guess the other thing I should have said here is that this is not true for quantum computers. You probably know that, right? These two problems, not hard if you have a sufficiently large quantum computer. So, there's a lot of panicking about that, as you could imagine. Okay, so this is going to be quantum key distribution, or QKD. So we're going to use quantum mechanics to get Alice and Bob to agree on the key. So here's how it's going to work. Alice is first going to pick. Alice is actually going to pick the key. Okay, so she's going to pick random. I don't know. Let's say K1, K2, K3. Imagine these are 3 random numbers. Okay. Then she's going to construct a certain quantum state, which I'm just going to sort of pictorially represent as follows. She's going to take a bunch of boxes, let's say 7 of them, okay? Each one of these represents some kind of quantum state, like a molecule or something. Let's not worry about what it is. Then she's going to randomly put these K1, K2, and K3 somewhere in here. Okay. We have ways of doing that. We have ways of encoding a number into a quantum state. So let's say she's going to put K1 in here, K2 in here, and I don't know, maybe K3 in here. Okay. Then she's going to set traps in all the other boxes. Okay, so she's going to put some kind of state in here. And then she's going to send the whole thing over to Bob. So now Bob has this same thing over here. Bob is going to reply back, and he's going to say, got it. Okay, just saying he received the transmission. That's important. And then Alice will send back the locations of the key numbers. So she's going to say, I put the 6, right? I put the key in positions 3, 4, and 6. Okay? So now it's clear how Bob can get the key, right? He just looks in positions 3, 4, and 6. He sees what those numbers are, and he gets K1, K2, K3. Let me informally and very briefly argue that actually nobody else can get the key. And here's the idea. The idea is that if you don't know, so, you know, Alice randomly selected the positions where she will put the key. Okay? So what are some things you could do? Okay? So if this was a classical piece of information and you saw it going across, one thing you could do is you could save it. Right? Wait for Bob to say, got it. Right? Wait for Alice then to announce 3, 4, and 6, and then look in your copy and find the key. Okay? But you can't. Okay? So you cannot copy this piece of information and save it for yourself to break it later. In some sense, you have to let it through. In some sense. Okay? Now, of course, you don't have to let it through. Another thing you could do is you could look at it. You could examine it. Right? You could shine a laser on it or something. Okay? So what would happen then? Well, because you don't know which positions have the key, what would happen? You would look here. You know, maybe you would or you wouldn't look, who knows. But because you don't know the positions of the key, it's almost a certainty if there's enough of these traps set that you will set off one of the traps. Right? Because anytime you look at one of these boxes, it changes by the no looking without disturbing principle. Which means that Bob, later on, I guess I should have said, check the traps. Right? That's essential. So before Bob declares, we're good, right? I've got the key and everything worked, he needs to check, are each of these question marks still in the same quantum state that they should have been at the beginning, right? And if they're not, he'll say, whoops, somebody messed with our state, right? So give up, okay? And by the no looking without disturbing principle, this should catch people who are trying to interfere with the transmission. So I think we're almost out of time, so I want to, hopefully this gives you some idea of what's going on in this area. Yeah, there's a lot more to say, but yeah. Questions?
I think we have another 5 minutes.
We do have another 5 minutes, but like I want to talk to you guys instead of just talking at you. So yeah, so I want to take questions or about this or in general. Yes.
Wait, so you said that someone can interfere, like with the transmission.
Yes.
Yeah. So couldn't they like overload the traps?
Couldn't they what?
Like set off so many traps that it just gets like too much to handle, like to check.
Well, I mean, Bob is just going to look at each of the traps, and as soon as he finds even a single trap that has been changed,
right,
a single state that has been changed, he'll say, okay, it didn't work, right?
Yeah.
I mean, I guess that's one sense in which this protocol is different from the math one. The math one kind of always works. There's no option for Alice and Bob to say, oops, that didn't work. For QKD, it's really important that Bob needs to be able to say, we give up. Somebody's interfering, somebody set off one of the traps, which means that they might have figured out what the keys are, so the process failed. Let's try again. Yeah. Yes?
What would a career look like in quantum mechanics?
A career in quantum mechanics?
Yeah.
So
what are typical pathways?
Yeah, so it depends. So if you really just want to study quantum mechanics, sort of the actual sort of field of physics, pretty much you're talking like an academic career, being like either an experimental or a theoretical physicist at a university. That's what most of the jobs are for actually just studying quantum mechanics. If you want to study like cryptography related to quantum mechanics, if you want to study like quantum algorithms, quantum computation, QKD, these sorts of things, then still you could be, work at a university. There are lots of like national labs that do research in these things, like National Institute for Standards and Technology, it's not too far from here, does. Now there are also a lot of companies that do it. Like IonQ is like a pretty famous company around here that does it. Yeah, so it depends a lot on what you want to do. Yeah.
I had a question specific to this, but
yeah.
So you said Bob would check the state of the traps and
Yes.
see if they're the same,
Right.
From what they were initially. But
Yes.
how would he check the states without disturbing them as well?
That's a great question. So, yeah, I mean, there's a lot of details here that I skipped. Part of the answer is that Bob knows how the states are set up. So, when Alice sends across this information, she's not just going to send the position of these keys, she will also send Bob some information about, what the actual trap states were. There's a lot more to it, but that's part of an answer. And remember that because of no cloning, that's not going to help the adversary, right? Like, if I send over the state, and then at some later point I send along a complete description of the state, like I tell everybody what it was, the adversary can't make use of that, right? Provided I don't, say what these values were. I want those to stay secret. Yeah. So yeah, sorry. Necessarily, every time I describe one of these things, I'm leaving out lots of detail because, yeah. More questions? Go for it.
This is the third method you said is the most modern, and is it are there any flaws in how that works currently? Like, have we found any flaws that would cause problems?
Great question. So QKD, so notice that this one, the math one was based on an assumption, right? The assumption was that this function is hard to compute. And that assumption turns out to be a little tricky, right? Because as far as we know, it's true for classical computers. Turns out it's not true for quantum computers. QKD is different. You can actually prove that just like we sort of proved that the one-time pad is perfectly secure, you can actually prove that QKD is also, in a sense, perfectly secure, assuming the laws of quantum mechanics. So there's no kind of assumption there. That doesn't mean that the scheme is perfectly secure in practice. In fact, there's people who do, they call it quantum hacking, who are able to actually figure out flaws in the hardware that's used to do this, right? Because in the end, this is done with some actual machinery, with some actual ion traps and lasers and single photon detectors and all this stuff. And these devices necessarily do not behave like this ideal picture. And so people can take advantage of those things and sometimes break them. QKD is actually used in practice, not nearly as much as the math approach. There are some, I think even since the late 90s, there have been some banks in Switzerland that use QKD to secure their channels. That is it, yeah, it is used. So if we had more time, I would love to talk about why the answer to this question is different from classical to quantum computers. It has a lot to do with linear algebra and signal processing and stuff like that for analysis. But maybe some other time.
Love to have you back.